Alright, so this is what we are going to do. So this is the figure we are going to do today. FOA assay to measure the function of various MSH2 mutants. Now this is your part of reading assignment early on. So this is the LBT, the wild type. Delta is the deletion of MSH2 that the vector controls. Those are various mutants. R542P, that's probably the last two, I don't remember. Those are just several mutants. Right, so the wild type should have, wild type MSH2 should have perfect mismatch repair mechanism. So when the perfect mismatch repair mechanism is there, what is this equation for? How many cells do we see? How many live cells?
A lot.
What?
A lot. Oh, you said in the wild type?
Yeah.
Oh, nothing. What's
nothing.
happening?
Yeah, there's actually nothing growing here. This is the complete deletion of MSH2. This one. Yeah, this one is a lot. So this is something called a negative selection. Why this is the case? Because it goes back to our basically the plasmid weight value. That's our reporter plasmid. The reporter plasmid has a Euro 3 with the microsatellite repeater in front of it. And that's the MSH2 PMSH2 plasmid we transformed last week. So this one has a history marker. This one has the tryptophan 1 marker. So the media we are in the transformation, we use a media which is minus tryptophan, How do I spell tryptophan? Sorry.
This why.
Minus histidine. I had to say it and then write it to get it right. Okay, so minus tryptophan we will select for PMSH2. Oh no, the other way around, sorry. And the histidine will select for PMSH2. Minus tryptophan will select PSH44. So, and then we use FOA. FOA is going to select for Euro 3 minus. If it's minus, it's going to live. If it's the Euro 3 constant, it's going to die. So, all right. So this one, FOA going to lead to this diet. This one going to lead to. Okay. So, all right. How could that happen? So now we always have a functional Euro 3. If it's perfect, so if it's perfect, everything is perfect. FOA should always kill the cell when growing. Sometimes we see a lot of colony. Why is that case? That's because we have a mutant MSH2 there. When the mutant MSH2 there is going to have a hard time to repair the microsatellite in front of it. With the microsatellite in front of Euro 3, if the microsatellite replication is a slippage, and then lead to the frame shift mutation Euro 3, and then we have a dysfunctional Euro 3. So the key idea is we have a bad MSH2. MSH2 is bad. How is that bad protein look like? Okay, let's look at bad protein. So, and then this one will lead to mutation in the microsatellite region, frame shift mutation. And then leads to the Euro 3 minus, leads to a. So if MSH2 is mutated, it's going to mutate a microsatellite in front of Euro 3, and then that leads to a Euro 3 protein which is mutated. And then the FOA killing effect will be blocked. And it will block this one. Block the FOA trying to kill the cell. So this one will kill the cell.
The mutation will? The mutant one?
Yeah, mutant MSH2 going to save the cell from dying. In this case, it's just the opposite. It's a negative selection.
Okay.
Yeah. So FOA going to kill the cell, but if Euro 3 is mutated, and then the cell won't be killed. So that's basically the idea. So then on the plate, you are going to have an FOA plate. FOA plate, and we're going to put what kind of sample, what's the appropriate experimental design we're going to put. We need positive control, negative control. We also need the mutant. So we have at least three: positive control, negative control, and the mutant you want to study. Every group has a mutant. So which one is our positive control?
The wild type?
Yeah, we need the wild type control. So we put the wild type there. Wild type and MSH.
But wouldn't it just be the control and not the positive control?
I guess, yeah, that's a wild, you can just call it a wild type control. And then we need a negative control or blank control. Which one would that be?
Is it a blank?
Yeah.
It'd be the mutant, right? The negative control?
No, you said like the blank.
Oh, nothing?
So that'd be the vector, like the
Very good, yeah, the vector. Yeah. The vector. Because if we really put it a blank, if we put a blank there, that means then we will miss the K3G on the plasmid. The cell basically won't live. Because the FOA plate is minus tryptophan minus histidine. So it has to have the histidine to live. You see the point? If we doesn't even put the plasmid there, the cell basically won't live. And of course, then what's the point to better function? Right? So it's actually just the opposite. So, and in our case, if we just put the vector there, the MSH2 will be basically MSH2 will be that deletion. There's no MSH2. There's no MSH2. The mismatch repair should have the worst function, and the mutation here should have a highest level, and then we see a lot of cells. That's for the vector control. If we don't even put a vector, there will be no HIS3. And the media is going to minus HIS3. Basically, no cell going to grow. It's just the opposite. If we don't even put the MSH2 there, unfortunately that's just kill the cell altogether. So that's what works. So we have to put the vector, just the vector, the PRS413 vector. Yeah. It's probably 413. Okay, you agree? Okay, thank you. Alright. That's our vector control. And then there's a mutant we want to put.
Yeah.
Mutant, what's your mutant?
422. I mean,
No, that's not the mutant, that's a strain name. What's the mutation we want to study?
Ours is MS371.
That sounds like
Oh,
a mutation.
AG371, I'm sorry.
That's wrong, that's a strain number. What's the mutation?
Oh.
If you look at the paper, how is the mutation described? That's R542P, that's what the mutation is.
oh, so everybody's gonna get the
Right,
same.
right, yeah. What's the mutation you are studying? Each group, write down the mutation you are studying. I'll figure out. That's actually part of your assignment.
Is it PSH44? Oh, no, that's not.
No, that's your report of passing.
Oh, wait, what?
What about H81Y?
H what?
H81Y.
H81? That's not right. That number, that's not right. That's not in the right place. That's the format is correct, but the information is wrong. So in any case, we need the mutant. I'm going to just write one. There is one mutation M707I, so that's one mutant.
Oh, D621N.
That sounds correct, yeah. So each group has their own mutation too, right? I'll just use one example here. So, and then on the plate, we're going to divide it into grid. For the what? So we're going to put the okay. So, well, let me recall this again. At least leave a voice record there. So the media recipe for the FOA assay is minus tryptophan minus histidine minus leucine plus FOA. It's minus tryptophan because on the reporter plasmid, the PSH44, it contains the TRQ1, which is the gene used to synthesize tryptophan. So we leave the tryptophan out, and then the cell has to keep the reporter plasmid, otherwise cell will not survive. It's minus histidine because we have the HIF3 marker on the TMSH2 plasmid, and the cell cannot synthesize histidine on their own, so they have to keep the TMSH2 plasmid in order to survive. And it's also minus leucine because the promoter PLE2 promoter is in front of the Euro3 reporter marker. We want to turn on the Euro3. And the Euro3 is like the light, the signal to indicate how well MSH2 protein going to repair this mismatch repair due to the microsatellite in front of it. The FOA is used as actual final selection. FOA, if the Euro3 is wild type, is going to kill the cell. If Euro3 is a mutant, and then FOA will not be converted into a toxic compound and kill the cell. So when the Euro3 becomes a mutant, and FOA cannot kill the cell will still be alive. So now on the reporter plasmid, though, Euro3 is wild type functional, but in front of it is the microsatellite. So microsatellite has a very high frequency to lead to a frame shift mutation. But when the MSH2 is functional, it's going to repair this. So for the wild type MSH2, the Euro3 is always most likely functional, and which means cell will not survive on the FOA plate. So for wild type, you'll see very few colonies here. For the mutant, when the MSH2 has some mutation, for example, each group have their own mutation to study. if the mismatch repair function is less efficient, then there will be high chance U3 will become mutant. And then FOA will stop the conversion of FOA to a toxic compound will be blocked and cell will live. So for the mutant, we will see some live cell here. But how can we tell the severity of the mutation?
The amount of cells there.
Yeah. We have the vector control. The vector have a complete deletion of MSH2. That one, so that's the maximal amount. How much damage can you do? That's the maximal amount. Right, so we have that as a scale. So that when this is completely deleted, U3 have the maximum chance to become a mutant, and so there's a maximum amount of live cell on this one, and then we can compare. So what's the key for this experiment to work? The amount of cell we put on the plate should be the same. You see the one? If we put more cells here or more cells here, less cell here, then it doesn't make sense anymore. The amount of cell we put on the plate should be the same. So then we can have comparison. I also have not discussed the host cell. If we want to do this selection, that means in the genome, nuclear genome, the host cell should be his minus, tryptophan minus, and also U3 minus. The host cell, its nuclear genome cannot have histidine, tryptophan, or U3, otherwise it also will not work. Because if it's a nuclear genome already have a U3, the cell will be killed as well. And we cannot use the tryptophan marker, we cannot use the histidine marker. So the host cell itself, those genes has to be deleted for this dosing to work.
D621. The D621.
So just to make it clear,
what's that one?
So I'm going to take a picture of this and so everyone should also write a summary of this in your notebook, and I will check this at the end of the class after participation break. You should write a summary diagram, the plasmid, what's a strand. Those are the yeast strands. Yeast strand. That's our media. This is our media we are going to use. And that's our experimental schedule, procedure. And that's the plasmid we're going to use. So you should write those in your lab report. Oh, in your notes, right? But of course, on your lab report, on your Google Doc, those information should also be there. That's really the key for the whole project. So let me erase this and make sure everyone is doing this right. On your plate, what you should be written is this. So I have a group 1. Which strand are you working on?
The one right there, M7079.
So it's AG371
Oh.
and the mutation is M707I. I for leucine. There is no amino acid called 1. So this is group 1. Group 2.
Is D621N. The strand was AG422.
AG422. D621N. Very good. Group 3.
Oh, we got 18.
AG91. This is G693D. Group 4.
We have, one on Benton. H658.
Excellent. H658Y. That's AG33. Excellent. Group 5. Okay. AG421. A61AB. Excellent. So those, you should put that into the mutant information. So this group 1, 2, 3, 4. Okay, so that's the group information. Dr. Kuber, how much, so when they start from,
So they, unfortunately, somebody broke that system, so we have to mix 2 or 3 trips to a microcentric. So, yank the plug and broke it. So you just cut it off and solder the plug.
oh, someone is spinning in an unbalanced way.
No, it broke.
Well, we just have more practice on centrifuge. Okay. Okay, let's start. So with the protocol is first we need to concentrate a cell. Our protocol it actually tells you. So you can actually officially calculate how much cell we need. But we are doing this in an approximate way. So we assuming the cell with the same OD has the same number of cells. So basically measure the OD, then concentrate the same amount of OD using optical density. What does the optical density means? We did this before. We also measure the optical density for nucleotide ion. But after we purify the plasmid, we use a nanojoule to measure the optical density at the wavelength 260 nanometers. And for cell number, for cell number, we often use OD 600 nanometers. So if we put this in a cuvette, the light will going to pass through. If there's a lot of cells, the absorbance will be very high. There's a lot of cell there. If it's very little cell, it's clear liquid, and then the absorbance will go down. So this is called absorbance. It's also called optical density. So this is kind of proportional to the cell number. It's just a convenient way to measure cell number. If we take the same number, so if we take say 3 units of optical density for all the cells, we assume they have the same number of cells. Okay. So we are going to spin them down in small Eppendorf tube. Here we spin on 3 mil.
Well, 5.
5 mil. Oh, that's quite a trip. Okay. But each time you probably can spin down 1.5 mil. So 3 times is about 4.5.
Yeah, 30 second speeds.
Yeah. So they can actually, technically they can spin down in 2 tubes and 4 times and twice. So let's spin down 3 times. Okay, yeah. All right, let's do this. We have a very busy day today. Yeah. So what we are going to do is
So just so you know what, because I could just, since there's few of them, I can just go downstairs, spin it,
spin a
the
lot.
swinging bucket, and then bring it back up.
Okay. Yeah. Okay. That's the same time. So
Because there's few of them in this section.
yeah. So we basically, according to the protocol, so that protocol has measured the absorbance of all the cultures.
Yeah, the whole first one is over there.
There's a mutation frequency, and in fact you can calculate the mutation frequency, and then from OD value estimate how many cells we need. Serial dilution, and then we just perform serial dilution.
So you already did the
Already did the absorbance.
Yeah.
the what?
The absorbance
OD
spectrometer.
value.
On our page, it says FOA protocol.
So I've given you enough cells to see some mutations.
Are we doing a 100 micron treatment or?
Take 10 of that.
I'm 75 weight. I mean, if you, but the first one will become 90.
Yeah.
Okay. Yeah. Okay.
There's still enough cells.
Okay, that's right.
Oh, because what you did in the morning, you just increased it a little bit to 110. The thing is, the pack cell board is retaining some water.
I expect that. So it will have 100 confidence. Okay.
You measured the absorbance already?
So you're going to spin the cells.
Yeah.
Oh, but what do we just?
So I'm going to go downstairs.
Yeah.
And why do you use the tube?
Because I just thought about it.
Oh, I see. Okay.
I was thinking that the others did in the morning. But somebody, they broke it after.
Thank you.
Yeah.
I know, I feel like dying. Is this water? I need gloves. I ain't touching no mutant niggas. Shit, you need no cold cancer. Where the gloves at? Over there. I'll put myself out like
So, okay, once again, particle is now spinning down the cell downstairs. So after spinning down, the water will be just decant, and then the cell at the bottom of the tube, we're adding 100 microliter of water to the tube, take everything, put it in the small appendix tube. So we should now have 3 small tube, wild type, vector, and mutant, all small in 3 separate small appendix tubes. Yeah.
Do we need to mix these up?
Yeah.
Small?
We need to
Mix it or centrifuge it?
What?
You want? Never mind.
Oh, sorry. But each sample is in a separate tube. We're not mixing those things now.
No. I was just like, do you want us to shake those small ones so that the solution and the water is mixed together?
Make sure the cell all goes through the water. Example, so basically the cell always resuspending liquid. And then we take 10 microliter of that into the next tube, which is labeled 0.1x. And then add 90 microliter water. That's a 0.1x diluted sample. Then do another 10x dilution, 10 microliter plus 90 microliter water, that's still 0.01x. So we do this for wild type, vector, and mutant. And at the end of this, we have FOA plate, put it horizontally on a desk, which you know it will not be shaken. This has to be because we are putting the liquid on each spot. If you shake it, the liquid is going to spill to the next spot. So the plate has to be absolutely still for at least half an hour for the liquid to be absorbed. You can only move the plate when it's dry. Otherwise, the whole experiment will be. So put I'll probably make sure there's a spot. I will not touch it or shake it, and just put it here. Not anything. Then drop after I add 90 microliter to the 9th spot, I just leave it there. At the end of the class, hopefully the liquid has dried, and then we put it upside down in the incubator. Yes.
Wait, Dr. What does that say? 10 microliters plus 90 microliters of water,
Yeah.
and then
The other one's 10 microliters of the second one's plus 90 microliters of water.
oh, okay.
And you start with 5 milliliters and then 100 milliliters.
No.
It's 100
I start with a 5 milliliter culture. I spin it down and just throw every liquid away. At the bottom there will be pallet of cell. I add 100 microliter of water to that.
And after you add the 100 microliters of water, you put that whole thing into
Appendix tube, a small tube, 1.5 mil, the white tube there. Yeah. That's the, yeah. So here go, the 5 mil tube is in this. This is called a Falcon tube.
100 microliter cell in this.
Yeah, in a small.
So you mix it up and so
Yeah, yeah. We need to mix them well.
into this. And then you dilute from there.
Yeah, to a full 10-fold dilution. 10-fold, 100-fold. Okay, yeah, you should have 9 tubes in front of you, all labeled.